Hi, I'm Eugene S. Canindot, and this is cs517A, Operating System and Networking. For this visual lecture, I'm going to talk about secondary storage structure. A secondary storage device refers to any non-volatile storage device that is internal or external to the computer. It can be any storage device beyond the primary storage that enables permanent data storage. A secondary storage device is also known as an auxiliary storage device, backup storage device, tier 2 storage, or external storage. So in one of our previous lessons, we talked about the memory hierarchy. We said that the topmost is occupied by the registers, and these memory systems are within the CPU. They are very small, but they are very fast, and they are expensive in terms of byte per pesos. The lower part are the secondary storage devices. They are less expensive, but they are much lower compared to the register, and these are these devices. The secondary storage devices primarily refer to storage devices that serve as an addition to the computer's primary storage, which are the RAM and the cache memory. Since they always consist of non-volatile memory, they allow the user to permanently store data on them. Typically, a secondary storage allows for the storage of data ranging from a few megabytes to petabytes. These devices store virtually all programs and applications stored on a computer, including the operating system, device drivers, applications, and general user data. They are used for a variety of purposes ranging from backup, data used for future restores or disaster recovery, long-term archiving of data that's not frequently accessed, and storage of non-critical data in lower performing, less expensive drives. The disk capacity during 1975 to 1989 doubled every 3 years. So there was 25% improvement each year, a factor of 10 every decade. So the growth or the increase in size is exponential, but far less rapid than processors' performance. This capacity during 1990s and more recently doubled every 12 months. So every year the capacity now doubles. There is now 100% improvement each year, and there's a factor of 1000 every decade. The capacity growth is now 10 times as fast as the processor's performance. So the hard disk has overtaken the processors 10 times over. So this is a graph showing you the increase in disk size from 1980 till 2019. Only a few years ago, disks are purchased by the megabytes. This happened like 5 years ago. We buy this by megabytes because those gigabytes disks are still very expensive. Nowadays, we buy disks by gigabytes, and they cost around 2,500 pesos per gigabyte. Actually, it depends. It ranges from 2,200 to 3,000 depending on the brand. This will translate to 2 pesos and 50 cents per billion of bytes. So imagine you can already buy billions of bytes, a device which can store billions of bytes for just 2 pesos and 50 centavos. So there was really a tremendous drop in price in terms of bytes, peso per bytes. There is a tremendous stride in making hard disks more affordable and at the same time increasing the capacity. So as you can see at the right, This is the a graph showing you the price per byte. So here there was a spike somewhere here. Oh, this one, Thailand flood. So there was a flooding in 20, that's 20 2011 2012, around that time. So I remember that we were panicking in the computer center because we there was really a shortage, because as you know, Thailand is one of the main producer of hard disks, and there was this flood and most of their facilities and factory at that time were affected. So there was a shortage, but eventually it tapered off, and as you can see, it continues to go down. So this is your hard disk. If you're going to open it, this is what you'll see inside. So the parts there, uh, there are major parts, and one of them is the platters. Platters are the circular disks inside the hard drive where the ones and zeros that make up your files are stored. Platters are made out of aluminum, glass, or ceramic and have magnetic surface in order to permanently store data. On large hard drives, several platters are used to increase the overall capacity of the drive. Data is stored on the platters in tracks, sectors, and cylinders to keep it organized and easier to find. And then you have the spindle, the one in the middle. The spindle keeps the platter in position and rotates them as required. The revolutions per minute rating determines how fast data can be written to and read from the hard drive. A typical internal desktop drive runs at 7,200 RPM, though faster and slower speeds are available. The spindle keeps the platters at a fixed distance apart from each other to enable the read-write arm to gain access. So this is one of the parts, delicate parts that that the engineers really have to compute. If they're going to run it, of course they can run it faster, but the faster they run the spindle, the less accurate they'll be able to read the data. So they have to balance speed and accuracy, because this is a mechanical device, not an electrical device. So that one is the read write arm. The read write arm controls the movement of the read write heads, which do the actual reading and writing on the disk platter by converting the magnetic surface into an electric current. The arm makes sure the heads are in the right position based on the data that needs to be accessed or written. It's also known as the head arm or actuator arm. There is typically one read-write head for every platter side, which floats 3 to 20 millionth of an inch above the platter surface. So there is a very, very small gap. This is microscopic in scale, 3 to 20 micro a millionth of an inch. The next is your actuator. The actuator, which is also part of your read-write arm or head actuator, is a small motor that takes instruction from the drive's circuit board to control the movement of the read-write arm and supervise the transfer of data to and from the platters. It's responsible for ensuring the read-write heads are in exactly the right place at all times. So these drives are addressed as large one-dimensional arrays of logical blocks. The logical blocks is the smallest unit of transfer. Low-level formatting creates logical blocks on physical media. So the one-dimensional array of logical blocks is mapped onto the sectors of the disk sequentially. Sector 0 is the first sector of the first track on the outermost cylinder. Normally sector 0, that's where important data like are placed. And since it's the first one, what the hackers before do is just change the value in the sector 0, and to fool the operating system or the computer of thinking that there is no data in your hard disk. That's what normally the hackers do. The old hackers, the old school hackers, they mess with the sector 0. So mapping proceeds in order through that track, then the rest of the tracks in that cylinder, then through the rest of the cylinders from the outermost to innermost. Performance depends on a number of steps. First is seek. Seek means moving the disk arm to the correct cylinder. Then you have the rotation. It's also the latency, which is a waiting time for the sector to rotate and rotate underhead. Then you have the transfer, transferring data from the surface to this controller. So the first two are mechanical in nature, and the third one is electrical. OS may increase file block size in order to reduce seeking. This is now OS trying to improve the efficiency of your hard drive. So it may increase the block size. But the problem of increasing the block size, you are actually introducing another challenge there. It's fragmentation, because if you're going to increase the block size, then there are smaller information, small data or small information that are placed in one block will not be occupying the whole block, and there are some spaces that are that remains. So it creates fragmentation. So there's a mathematic here. You wanted to be more efficient by increasing the size of the block. It will become efficient, but at the price of having more fragments. If you decrease the size, less fragment, but your disk will be less efficient in reading. OS may seek to collocate related items in order to reduce seeking. Okay, so you are going to collocate related data in one block. So this is also one of the strategies that can be done to improve performance. This scheduling is done by operating systems to schedule I/O requests arriving for the disk. This scheduling is also known as I/O scheduling. It is important because multiple I/O requests may arrive by different processes, and only one I/O request can be served at a time by the disk controller. So we have already talked about scheduling. This happens because the processor are doing something else, and all these requests has to wait before they are being served. So there should be a scheduling to have a smoother operation within your computer system. So you also made a report on this. This is the reports that you did is similar in concept, as you will see later on. So these scheduling algorithms. So you have the first come first serve. It's reasonable when load is low, but long waiting time for long request queues. Short seek time first, or SSTF, minimize arm movement and maximize request rate, but unfairly favors middle blocks. So you could imagine that since it's shortest seek first, so always you are lucky, or the data is those data that are in the middle of your platters are normally the lucky ones, because they are the nearest to be read. The next is scan. They also call it elevator algorithm. Service request in one direction until done, then it reverses. Skews wait times is not uniform. So you will imagine that it will go from left to right, and then it will go back right to left. So the skew time is not uniform. The next one, the C-scan, you have a uniform skew skew times. So like scan, but only go in one direction. We'll have uniform wait times. And then you have the C-look, similar to C-scan. The arms or the arm goes only as far as the final request in each direction. So now it will no longer go all the way to the extreme direction, but it will only go to the to the last data as far as the final request in each direction. Shortest seek time first is common and has a natural appeal because it's easier to implement mechanically. Scan and C-scan perform better for system that place a heavy load on the disk. Performance depends on the number and types of requests. So normally it really depends. Then requests for this service can be influenced by the file allocation method. The disk scheduling algorithm should be written as a separate module of the operating system. So as of now, the disk scheduling is already lumped. It's already part and parcel of your operating system. So there is a move to separate it and separate component so that it will be easier to replace should there be a special software or there is a special thing that you want your computer to do, so you could easily replace the disk scheduling algorithm. Next is solid state drive. The standard HDD or hard disk drive has been the predominant storage device for computers, both for desktops and laptops, for a long time. The main draw is the high storage capacity and low cost. The SSD, solid state drive, is another storage solution. It is a disruptive solution and is slowly replacing the majority of hard disk drives. There were several technical comparisons made by computer scientists, and the SSD is the clear winner in most of them. However, due to its price per unit of memory, it doesn't make sense to use SSDs in all instances. For most computer users, it is recommended to use SSD as the primary drive for the operating system and the programs that are accessed most frequently. Then it is suggested that a large HDD, either internal or external, be used for storing documents, pictures, and music. To recap, the OS manages another important component of the computer system, which is the secondary memory storage. A secondary storage system is necessary because the memory or the primary storage cannot retain data when the computer is turned off. The secondary storage system allows computers to be more versatile in that they do not need to have their hardware reconfigured for each new program, but can simply be reprogrammed with instructions that are saved in the secondary memory. So for recommended viewing and reading, please visit these sites. So you have two YouTubes there. They are interesting to watch. And with that, I thank you for listening to this video and watching and listening.